Hi, today I'm going to talk about some basic concept in linear algebra. So first of all, let's take a look at this matrix A here, where we have 3 rows and 4th column. And also let's take a well, if you take a careful look in this matrix here, you will notice that not all the matrices are linear independent. So you can see that the 4th column are literally identical to the 1st column. And then the 3rd column is actually the sum of the 1st and the 2nd column. So that the 3rd column and the 4th column can be achieved by some linear combination of only using the 1st and the 2nd column here. So that we notice that not all columns are linear independent now. So we can also verify this by taking a look at the row reduced echelon form of the same matrix, and then we can see that by looking at the leading the columns with leading numbers here, we can notice that only the 1st and the 2nd column are called the pivot columns, since there's a leading number at the first non-zero entry. And again, the 3rd and the 4th column can be achieved by some linear combination of the 1st and the 2nd one. So that it tells us that the 1st and the 2nd column are the pivot column, and then the 3rd and the 4th column has the free variables here. So we can calculate the rank of this matrix is equal to 2. So the rank of the matrix is equal to the dimension of the column space, and is also equal to the number of the pivot column. So the pivot column is thus the 1st and the 2nd column. So the rank of the matrix is equal to 2. And the column space is actually a space that is spanned by the columns here. And the two linear independent columns is the first 2 columns here, so that the column space that is for this matrix is just is spanned by the 1st and the 2nd column, so that the dimension of the column space is actually the 1st and the 2nd column, so it's also a 2 here. So the column space can also span by all 4 columns actually, but since the least number of the vectors or the columns that we need is the 1st and 2, since if we use first 2 columns to create a column space, then the 3rd and the 4th column is also within the same column space. So we don't need to use this all 4. We only need to use all the first 2 columns, and then we can create a column space that already contain that the 3rd and the 4th column are already within the column space. So that's why the rank of the matrix is equal to 2. That is also equal to the dimension of the column space, which is spanned by the 1st and the 2nd column. And then the number of the pivot columns are, we can see that in the row reduced echelon form of the same matrix is actually the first 2 columns as the pivot column. So that it also verifies that the rank of the matrix is equal to 2. So now let's take a look at the null space. So null space is actually the set of all possible solutions that makes AX equal to 0. So if we have x here, and if a x can make if multiplied by this matrix A and return the 0, then that x is fall into this null space. So now let's take a look at some particular matrix vectors in the null space. So one way to calculate the null space, one vector in the null space is that we set, in our case, since there are 2 free variables here, so we put we assign 1 to one of the free variables and then 0 to all others, and then we can keep doing that, and then to find in our case 2 particular vectors in the null space. So for example, if I put 1 to x3 and then 0 to x4, so we can get so 1 plus 0, and then so that's we put the -1. So if we put so if x2 is -1, then -1 plus multiplied by 1 plus 1 times 1, and then plus 0 0 times 0, and then we get 0. So that we can actually delete this. So if we plug in 1 and 0 to x3 and x4, and then in order to get a 0, and then so that we need x2 to become -1. And now we plug in -1 multiplied by 0 is 0. 1 plus 1 multiplied by 1 is 1, and then a 0 multiplied by 1 is 0. So 0 plus 1 plus 0, and then we also plus 1 times x1, and then return 0. So x1 should also be a -1. So now if we use a multiplied by 3, 1. So again, this vector is within the null space. So null space is all the solution that gives ax equal to 0. So by using this column multiplied by matrix A, so this should return 0. Yeah, so as you can see that this vectors is within, so it's one solution in the null space. So now let's exchange so now let's assign 1 to x4 and then 0 to x3. And then we can also do the same calculation. So 0, so start from the last column that has a leading that has number in it. Since the third column is all 0, so we can disregard that rows. So 0 plus 0 plus 1 x1 equal to 0. So x1 should be 0. So that's 0 here. And then if we plug in onto the first row now, so 0 plus 0 plus 1 plus x1 equal to 0. So that x1 should be -1. So that's our solution for another vectors in the null space. So now let's verify. So if we multiply by 3, 2, it should also returns 0 here. So here, so 3, 1, and 2 are two specific vector in the null space. And the null space is also, since they are linear independent between to each other, so that the space that is spanned by these two vectors are also should be the null space. So we can do any linear combination of these two matrix, these two vectors, and then the space or the solution should be in the null space. So here, so for example, I create two random numbers and then giving them a random linear combination here, and I store that into the object called null space. So and then I use a multiplied by the null space. So again, that should also return 0. So now let's run. So as you will notice here that every time I run the runif, the null space is actually changing, as you will notice here. So I get another set, and then I get this. I still get a 0. I get another set of a linear combination, and then multiply by a again, and then still get 0. So that means all the linear combination of these two vectors, and then is in the null space. So that's why I use a multiplied by the null space. I still get 0, no matter what numbers I put as the coefficient here. So that is the definition of the null space. So the dimension of the null space is just the number of the free variables. So by looking at the row reduced echelon form, so third column and the fourth column has the free variables. So that the dimension of the null space is also a 2. And the basis of the null space, since these two are linear independent, so that the basis of the null space is just these two. So for the basis of the of any space should be first should satisfy two conditions. One is that they should be all linear independent to each other, and then the second one is that they should span a space. So a null space is already a space. So the basis is that a two vector that are linear independent. So that's the definition or the concept of the null space. And now let's take a look at the basis of the column space. So as we discussed before, the column space is actually just the first two columns since they're in the pivot column. So again, they are linear independent. So the first rule is that they must be linear independent, and then the second rule is that they must span a space. So the first and the second column are the basis of the column space, and these two vectors are the columns are the basis of the null space, where null space is that ax all solution to ax equal to 0. Okay, so we talk about the basis. And now let's talk about solving a linear system. So that we have solving ax equal to b. Okay, so here we have a matrix. It's called matrix A, and then the numbers is called the B. So basically, a matrix is just another way to write a linear system like 1x1 plus 2x2 plus 1x2 equal to 2, 3x1 plus 8x2 plus 1x3 equal to 12, etc. So it's just another way. It's just another representation of a linear combination. By doing some manipulation of the matrix, we can solve a linear linear system easily. So here we have ax equal to b, and then if we can find an inverse of the matrix A, and then we multiply on the left hand side on the left side of both sides of the equation. So inverse of A multiplied by A multiplied by x, and then it's equal to inverse of A multiplied by B. And then inverse A is just the identity matrix, so that the left hand side is left with x on the left hand side, and the right hand side is just A inverse B. So in R we can calculate the A inverse B by calling the solve. So that is actually the inverse of A. And then we use the inverse of A multiplied by B. So that will be the solution of our of x. So now let's take a look. So we store the x by in this we call the x solution, and then we use ax, a times x, and then so the result should be the b vector here. So now let's take a look. So that the calculation by using a multiplied by the solution is 2, 12, 2. So that also verify that x is the solution for this linear system. Okay. So now also take a look at the rectangular matrix. Since that means the number of rows and the columns are not identical. So here we also have an augmented matrix here, where we bring the the um, the constant term also into the matrix. So that means 1 times x1 plus 2 times x2 plus 2 times x2 plus 2 times x4 is equal to 1. And then 2 times x1 plus 4 times x2 plus 6 times x3, and then 8 x4 equal to 5, and etc. So we bring the right hand side of the equal sign also into the matrix here. Okay. So now let's create create a matrix here. So that is that the matrix A with B as in the last column. So here let's talk about the I think it's called the Gaussian elimination. So the Gaussian elimination can be also calculated in by multiplying a matrix by matrix multiplication. So here, first of all, we create a identity matrix here, and to do a Gaussian elimination, and then we just keep reducing the numbers in each row. So here we have so we can leave the first row as it is, and then we notice that the first entry in the second row is a 2. So we want to reduce want to reduce 2 times row 1 from the second row, so that we can achieve by getting a negative 2 in the first entry of the second row. So if we multiply that E21 by to matrix A, and then the rest is actually an identity matrix, but we put a negative 2 in the first entry of the second row. That means we want to reduce, we want to subtract 2 times the first row from the second row. Okay, so let me first clear everything and then just to make it clear. And that's our matrix A with the vector B. And then we also create a elimination matrix here, where we want to do the Gaussian elimination in the matrix format. So again, we want to do minus 2 times the first row from the second row. So here, if we do that, you will notice that this return exactly the result where we want to subtract this 2 times the first rows from the second one. So 2 minus 2 times 1 is 0, and then 4 minus 2 times 2 is 0, and then 6 minus 2 times 2 should be 2. So here we have a 2 here, and then 8 minus 2 times the 2 is a 4, so we have a 4 here. So 5 minus 2 times 1, so we have a 3 here. Okay, so that's our first elimination matrix by subtract 2 times the first row from the second row. And after the first elimination, and then we also want to subtract 3 times the first row from the third row. So we put a negative 3 inside identity matrix, and then we create that E31. So that means elimination between row 1 and row 3, and then we multiply by E31 to the result of E21 times multiplied by A, and let's see. So that from here we multiply 3 times row 1, so 3 minus 3 is 0. So 6 minus 3 times 2 is 0, so that we have 2 leading 0 here. And then 8 minus 3 times 2 is that left with a 2, and 10 minus 3 times 2, so that is 4, and then 6 minus 3 is 3. So after the second elimination, we get this result here, and again we want to minus. So our last step between third and the second row is that we want to subtract the third row 2 from row 3. So we put a negative 1 here. So that means we want to subtract a row 2 from row 3. Okay. So by multiplying everything together, that should give us actually a upper triangle matrix here. It is not the row reduced echelon form yet, since we still need to do something from beyond this part. But this will give us a upper triangle matrix here so far. So and then that will also make our calculation easier. So that yeah. So by doing all the elimination step and then multiply by A, and then we get an upper triangle here, so we call it U. And there's also a factorization called LU factorization. So L is a lower triangle matrix, so that is 0 on the top, lower 0 above the diagonal, but numbers below the diagonal. And that factorization is actually that the L is actually just the inverse of everything in the for the elimination matrix. So so we have already created the elimination matrix here, and then we can take the inverse here. So let's take a look at the L. So L is so this number should be a zero. It's just a very small. So that's why it is a lower triangular matrix, and U is the one here. So it's an upper triangular matrix. So if we multiply L to U, and then we should actually get the matrix A here. So first do so the so first get the elimination matrix here, take the inverse, that will give us the L. And then the U is actually the elimination matrix and then multiply by A. So the result for LU is actually the A. So this is called the LU or LDU. There's some you can also factor out the diagonal of the U matrix here. So this is called the LU factorization of matrix A, so that the left hand side is equal to the right hand side. And then to get this factorization is that you need to get the inverse of all the elimination step in the Gaussian elimination. So that is called the LU factorization. And then I also demonstrate that to do the Gaussian elimination in the matrix format. Okay. So now also let's take a look at solving a matrix that has more than one or more than one unique solution. So yeah, again we are still solving the same matrix here. So this matrix is actually 3 by 4 matrix, and then B is actually the fifth column here. So that's the coefficient, and then that's the constant term. And now let's solve this matrix. Since there are 3 variables here, and so that means there's no unique solution. So there are infinite many solutions here, but we need to find a way to represent the solution. So again, we can so now let's take a look at the particular solution of this linear system here. So the calculation to do that is that we set all the 3 variables to 0. So by taking a look at this matrix after the Gaussian elimination, we will notice that the first and the third column are the pivot column, and then the second and the fourth column are the free has the free variables. So by calculating the x particular, we set all the free variables to 0. So we put x2 and x4 to 0. So x4 is 0. So 2x3 is equal to 3. So x3 is equal to 3 divided by 2, 1.5. And by plugging, so that's 3 plus 0 plus 0 equal to 1. So x1 is just using 1 minus 2 times x3, so that we have 1 x1 x2 x3 x4 here. So the free variables we set it to 0, and then the pivot column we have -2 and 1.5. So now we use the solution the solution we call it x particular, and then we multiply by that, we get 156 here. So that is one particular solution of this linear matrix. So that this x1 x2 x3 x4 multiplied by the coefficient, we get 156 to the so that's the particular solution. So that is one of the unique solution. But since we have three variables in this system, so that means there are also some other combination, or there are also infinite many solutions. So for in that case, to get a complete solution, we also need to get the null space of this matrix. So notice that A times x particular that we just verified, we get the B, which is the constant term. And we also just talk about the null space. So A multiplied by the null space is returns 0. And now if we take the sum of these two functions here, so A times x particular plus A multiplied by the x null is equal to B times B plus 0. And then we can also using the distribution rule, we have A multiply x particular plus x null, and then it's also equal to B. So that a complete solution is that x particular plus the vectors in the null space. So x null is that all the vectors that multiply by the matrix and then returns 0. So now to get the null space, so again, null space is a linear combination of two bases of the null space. So now we need to calculate the basis of the null space, which means two vectors, they should be linear independent. So by using the same technique we use over here to calculate the two free variables here, and we set one free variable to 1 and then 0 to the other, and then we can calculate from this function here, so that disregard the fifth column, since right now we want to calculate the ax equal to 0, not ax equal to b anymore. So we want so 0 plus 0 plus 2 times x3 plus 4 times x4, 0, should be 0. So that x3 should be 0 divided by 2, so it should be 0. And then I will skip the step, but so just using the back substitution to get 1 times x1 plus 2 times x2, 2 times x3, 2 times x4 equal to 0. Where given that x2 is equal to 1 and x4 is equal to 0, and then here we get one of the solution, one of the vector in the null space, and then we assign assign 0 to one of the free variables and 1 to the other free variables here, and then we use the back substitution, and then ax equal to 0, and then we get x3 and x1, and here is another vector in the null space. So the null space is just a space that is spanned by two bases of the null space. So you can check to see if they are linear independent, and then any linear combination of these vectors should be in the null space. So we can also verify that by, for example, using A multiplied by x null 1. Let me store everything, and then use the coefficient only, since our A is augmented matrix where we also include the coefficient, the constant term here. So here, so this vector multiplied by the coefficient, we get 0. We use this, we check on the second vector, we also get 0. So we verify that these two vectors are in the null space. And now let's take a look about the linear combination of these two vectors. It also returns the 0. So every time I run the R uniform function, I create a two unique number. So we can keep testing to see they all return 0. So that means all the linear combination of these two matrices are also in the null space. So finally, the solution is actually the x particular plus the vectors in the null space. So where we already proved or verified from here. So that's our complete solution. So now let's store the solution into this object, and then let's see. So if we keep refreshing, we still get 156, 156. So any linear combination of the null space and then plus the x particular will return is the final solution for this linear system. So again, let's take a look at the matrix A. So that any solution, so any combination of the null space plus the x particular, and then we multiply by the coefficient, which is the first 4 columns, it will return 156. So that is the complete solution for ax equal to b when there are infinite many solutions for the ax equal to b, unlike the part in here where there's a unique solution. So to get so there's also some rules to talk about to check whether this equation has no solution or one solution or infinitely many solutions. So that will depends on there are some rule to talk about that. But that's it. That's all the basic concept that I want to talk about in this video. So thank you very much, and let me know if you have any question.